Welcome you all once again. And today I'm going to discuss about the question bank. Okay, one of the question from the question bank based on mood detector. Okay, mood detector using sequential logic techniques. So far we have discussed many questions, right? Many questions on based on different levelings. And now today we will discuss mood detector. Okay, mood detector based on the sequential logic. So in the sequential logic topic, we have discussed different types of machines. Okay, we have discussed the asynchronous and synchronous sequential machines based on the time constraints. The synchronous sequential machines are the work under based on the time constraints, whereas the asynchronous sequential machines, they don't consider the time constraints. So here, based on the question, so here we have a question: write a Verilog code for 1011 mode detector and also obtain its test bench and simulation result. So here, if you observe the question, what are the things we have to look into it? Is first thing is we have to write a Verilog code, and that Verilog code is to be meant for 1011 mode detector. So for this 1011 mode detector, we have to frame a Verilog code, right? And also the Verilog code and followed with the test bench. And before moving on to this detector or also mood detector, just recapitulate. Okay, we just recapitulate whatever we have studied in the sequential logic. In the sequential logic, we have studied about different machines based on the synchronous sequential and few machines based on the asynchronous sequential machines, right? So in that and also we have discussed about the finite state machines, FSM, finite state machines. So and also we have discussed about the Moore and Mealy machine. So out of this all things, see in the overall, we understood one thing, that all these machines, they works under one thing, that is a states. Okay, so state transitions. For the purpose of state transitions, we are considering different machines. Okay, and different machines have different specifications. For example, if you consider the Mealy and Moore. Okay, if you consider the Mealy and Moore machines, we say that in the Moore machines, the output depends only on the present inputs and as well as present inputs. Whereas in the Mealy, we consider the outputs output depends upon the present inputs and as well as the past outputs, right? And also when you compare this Mealy and Moore, we see that Mealy is the better machine that we can consider. Okay, if you consider these two, in all the efficiency purpose and also the time considerations and the delay, in all these things, we can say that the Mealy is the better one to go. And now we will see that coming to the problem 1011 mood detector. Okay, so we have seen, or else we have discussed about the sequential detector or the sequence detector as well, right? So what is this 1011 mood detector is all about? So here, the Moore FSM, the finite state machine pertaining to this Moore, it keeps detecting a binary sequence from a digital input and the output of the SMS, where it goes high only when 1011 sequence is detected. So here, what this 1011 mode detector is talking about? It says that the FSM, the finite state machines, they do get the output, and sometimes what happens is the output, there's a chance of outputs, the FSM, the finite state machines, the output of the finite state machines, they may go high. Okay, at what extent they may go high is at 1011. Okay, at 1011 is a sequence where the output goes high. Okay, this is what we can see in the finite state machines. And now the state diagram of Moore FSM, as we are considering our question based on mood detector 1011. So here the FSM is a sequence detector, 1011 is for the sequence detector, and it is noted that Moore FSM output depends on only the current state of the FSM. So here, as we have differentiated the Mealy and Moore, okay, as we have differentiated the Mealy and Moore, the Moore state that the output is considered only on the current state of the FSM, only on the current inputs. Okay, only on the current state of the inputs. So the state diagram of Moore FSM for the sequence detector is like this. See here, we have 4 states. Remember that in the state machines, state is considered as the circle, right? So this is a state. I have a S1, S2, S3. These are the states. Okay, we represent the states in a circle, and then these are the direction lines, right? So these are the direction lines. Direction line states that when the transition is taking place from one state to another state, that is how through the direction lines we are representing, right? So the direction lines S1 and S2, and also you have like this 1/0. So it's sometimes 1/1. So what is this 1/1 is one before the slash. Okay, the digit before the slash is nothing but the input, and the digit after the slash is nothing but the output, right? So this is how we are going to represent the states and the transitions, and as well as the inputs and as well as the outputs. And now this is a more FSM, where here we have the 4 states: S0, S1, S2 and S3. Okay, so for more machines, remember that in the state itself we are representing the in outputs. That means what? S1/1. That means it states that S1 is a state and 1 is the output. So if output is 1, how the state is going to take its transition from which state to which state? That is what we have to do, right? So this is about the Moore FSM. So here we have S0, S1, S2 and S3. So the state transition, the transition from S0 is going to S1 is with respect to 1. That means what? When the output is 1, my state is going to take its transition to S1, whereas the input is 1. And similarly, if my output is 0, what happens is my output is 0, whereas my input is 0. Okay, when my output is 0, my input goes 0. When my input is 0, it means that the state is not taking its transition, but it is going to remain in its own place. Likewise, see, this is how. And then if my output is 0 and then my input is 0, if my output is 0 and input is 0, what happens is then the transition is going to take place from one state to another state, that is from S1 to S2. See here, my output is 0 and also my input is 0. When my both input and output is 0, it's taking its transition from S0 to S1. And for example, when my output is 0 and the input is 1, okay, then how the transition is taking place is, it's not getting transition, but the state is going to be itself in the same place, idle state, S1. Okay, so this is how the mechanism goes on. Remember that in the Moore statements, based on the output, the transition of the transition between the states takes place. Okay, so this is one of the important point to be noted. If you want to differentiate the Moore and as well as the Mealy, and this is a Moore machine. So we know that these are the transition logic. Okay, input side you have a transition logic, and output side you have a output logic, and in between you have a state memory. Okay, this state memory consists of the flip-flops registers as well, okay, to store the data or the information. And also we have, there is a connection between, among all these 3 states, that is state logic, state memory, transition logic, and as well as the output logic. Okay, the input is given directly to this transition logic, whereas it takes its transition based on the based on the inputs and outputs that is having, okay, in the memory, so that based on the transition, based on the input, okay, the state takes its transition and gets the output, okay, the G. And here for each the state memory, as it is a memory, we know that we have the clock. Okay, clock signal is present. Okay, when the clock is present, we know that the set and reset pins are available for each and every clock. And see that based on the state, if this transition is taking place, what happens is, again it has to go for the input. It has to take it, or else it has to consider the input, so that it has a feedback. Okay, it has a feedback from the as soon as it give its transition, the state output, what happens is it's taking its transition towards, or else a feedback again to the transition logic. Okay, so this is what we can see in the diagrammatical part. That means, so likewise, S0, S2 and S3. Okay, these are the direction lines, 1, 0, 0, 0 and sometimes 0, 1. So this is purely what how can I say, this is a Mealy. This is a Mealy mission. Why Mealy mission? Because here in the states we are not mentioning any output. In the Moore mission, we are mentioning the output itself in the state, along with the state. So here it is a meal emission. This is how the transition taking place from S1 to S2 based on the input. The output you are going to observe as 0. So the whole mechanism, whatever we discuss with respect to the state diagram, this is nothing but the state diagram. Using the state diagram, this is the block, in a diagrammatical way we are representing over here with respect to the input transition logic and also with respect to the output logic and state memory. And now, Moore machine is finite state machine. We know FSM, Mealy and Moore are finite state machines where in which the next state is decided by the current state in current input signal. So, in the Moore machine, we know that the next state is going to decide it. Okay, the next state is going to decide based on the present input. Okay, based on the current state and the input, current input and as well as the current state. Okay, then the output symbol at any given time depends only on the present state of the machine. So, the output is going to be determined only with respect to the present state of the machine. And this is a code. In the question, it's mentioned that write a Verilog code for 1011 Moore detector, right? So, this is a code goes like this. Model instantiation. This is the very first and the foremost thing, model instantiation. And the name is sequence detector. More in the Verilog we are writing, and it is a port list. So what do we have in the port list? We have in the port list a sequence in clock, right? Reset, detector, out. Okay, so these are the things that we can observe or is as an input and output, and also the in output that is to be mentioned in the port list. And then coming to the declaration. Okay, we are declaring here the input and as well as the output. So my inputs are clock signal, input reset is reset input sequence is binary input, right? Output detector, output register is detector output, that is output of the sequence detector, that is output. And then the parameters, that is 3 bits of 0, 0, 0, 0. So we need to go that 1, 0, 1, 1, right? So how many bits is a 3-bit binary code? Okay, 3-bit binary code. So 0, 0, 0. So 0th state. So this is all about the 0th state, and it's a 1 state, and 0, 1, and 0, 0, 1, and 0, 1, 0, 0, right? So first is we are going with the 0, and we are going with the 1, and we are going with 0, 1, 0, 1, 1, 0, 1, and we are going with 1, 0, 1, 1. Okay. So this is what? So 0, 1, 1, 0, 1, 1. Then finally register, it's a 3-bit of state, current state. The next state based on the next state is going to be determined based on the current state and the current input. So register and the sequential memory of the Moore FSM. So how the sequential, see in the sequence wise, that means what? First we have to detect first bit, and then along with the 2 bits, and then along with the 3 bits, and then along with the 4 bits. So sequence detector, it says that we are going to detect the bits in a sequence manner. So how is sequential memory of a Moore FSM? So our code is purely in the behavioral modeling. So as we are writing our code in the behavioral modeling, then the keyword is meant to be assigned as always at the rate positive edge clock. Okay. Also, one of the advantages by considering this code in the behavioral modeling is we have the memory element, right? So each and every memory element are followed with the clock signal. So likewise, always at the rate positive edge clock and positive edge reset as well. And then begin if reset is equals to 1. And now we are starting our code by saying the begin if reset is 1. When if reset is 1, what happens is the current state less than or equals to 0. Okay. When reset is 1, what happens is the FSM, when the reset is 1, when the input is reset is 1, we get the FSM. The final state machine gives the output as 0, right? 0. Then else, if reset is, say if current state is less than 0, then we are going to observe as 0. And if not, okay, if else, if my current state is the next state, if it is the next state, what happens is otherwise the next state. If, say 2 conditions we have to consider. One is, if it is with respect to 0, okay, then the output goes as 1. If not, the next state. If not, the next state. So these 2 are the conditions to be followed. And then finally, and combination logic of Moore FSM to determine the next state. Now, in order to determine the next state, how is always at the rate current state sequencing. Okay, current state sequencing, then begin, and now the case statements. Okay, conditional statement and along with the case statements follows. Case current state 0, current state is 0, and now begin. If my sequence is 1, okay, if my sequence is 1, what happens is next state begins, next state output goes as 1, and then if not, my next state is 0. That means what? If my present state is 0, there are two conditions, or else there are two things that we can observe. My next state would be 0 or my next state would be 1. So previously also we have discussed this, no? When my input is 0, what happens? My next state would be 1 or the next state, right? So here as well, and then if it is 1, okay, 1 begin. That means what? Here we are going to detect this bits in a sequence manner, 1 0 1 1, right? So first we are going to detect 1, and then we are going to detect 1, and then 1, and then 1. Okay, so for the step 1 we are going to detect 1 as single, and the step 2 we are going to detect 0 as 1 0, and in the third bit, in the step 3 we are going to detect the bit as 1 0 1, and the fourth step we are going to detect the bits as 1 0 1 1. Right? So here 1 begin. If my sequence is 0, if my sequence is 0, my next state will be 1 0, or it would be 1. Okay, 1 0 1. If it is see here we have decided that if it is 1 and 0. Okay, this part is we have discussed 1 0, and here it is 1 0 1. Previously what it is only 1, right? So we have done with the 1. We have done with the 1, and second is 1 0, that is 1 1 0 is done, and the third bit is 1 0 1 is also done, right? And then fourth, finally, if it's 0, what happens is next to 0 is 1 0 1. Okay, 1 0 1, and then if it is 1 0 1, if it is 1 0 1, then how are we going to detect the last bit is, if the condition, if it is 0, one thing is we are going to observe as 1 0 1 1. See, the next state would be 1 1. So one thing you have to remember, that the present state is 1, the next state you are going to observe as 0, and the third state is you are going to observe as 1, and the fourth state you are going to observe as 1. Okay, so likewise we are going to detect the sequence by using the case statement or conditional statements, if else if, right? Then finally what happens is, here the next state is 0 1 1 0 1 0 1 1. So this is what we are going to achieve with the final state. So by default the next state would be obviously 0, and then finally the terminating our code with the end case and then end module. Okay, end case and then end module. So I hope you understood this. First time, see here, we are detecting 1011 Moore detector, right? So we are detecting 1011 Moore detector. In the Moore detector, we are just representing, initializing the module instantiation has to be done. First thing with the name and the port list, and then input output declarations, and then coming to the case sensitivity list. So the sensitivity list is all about the behavioral modeling. You are writing your code in the behavioral modeling, right? So always at the rate POSIX is a sensitivity list. So in the after the sensitivity list, we are moving on to the statements, right? In the statements, we have to be very particular. Okay, we have to be very particular in how, in what way we are going to achieve this 1011. So we can write, we are going to achieve this 1011 detector by using the case statements and conditional statements. By using the case and the conditional statements, we are going to achieve our goal. So here by using the case statements, always begin and if else if. So finally one after the other. First one we are going to observe 1, okay, and then 0. And by clubbing 1 0, we are going to observe 1 0 1, and then finally 1 0 1 1, right? So after this, this is what finally we are terminating up with this end module. Then after writing the Verilog code, soon after you have to write the text bench code as well. So in the text bench code, how are we writing is simply mentioning the module instantiation of the module, and then the instance name followed with the port list. So here we are representing the inputs and as well as the outputs. So our inputs are sequence in clock and reset, and our outputs are as detector out, and then instantiating the sequence detector using more FSM. So here whatever in the Verilog code we have discussed, okay, each and everything in a sequence manner. First we have observed 1 and then going with 10 and then 101 and then finally 1011, right? And so here initially beginning the clock signal 0. So now in the test bench vector, how we have to represent the delays, okay? So with how much of delays the output is going to observe. So in order to detect the next bit with the 5 nanoseconds of delay, the clock signal with the 5 nanoseconds of delay, I am going to observe my output as 1. Okay, this is what initializing the resetting of the bits as 1. So likewise, for 30 nanoseconds of delay, 10 bits 1 0 1 1, right? So for 30 nanoseconds of delay, the second bit, the third bit is 40 nanoseconds, and the fourth bit is 20 nanoseconds, and 30 nanoseconds, 10 nanoseconds. Likewise, after completing the sequence, we are adding, we are finally ending up or else terminating our code with the by using the keyword end, and then all finally terminating our whole code by using the end module. Okay, so this is how we can write the test bench for this more FSM sequence detector. So in the exam point of view, from the sequential logic, okay, from the sequential logic, if you come across any question based on the numerical part saying that write a code based on 1011, okay, 1011 FSM detector or else 1011 mood detector, the only thing is you have to first and foremost thing is you have to write down what is Mealy mission or else what is Moore mission. Before writing Mealy and Moore, you have to mention what are these missions, FSM, finite state missions. Mention FSM clearly, write the definitions, and then go off with the different kinds. Okay, FSM, under FSM we have Mealy and Moore, and then you have to mention what is a Mealy mission and what is a Moore mission, and then you have to differentiate between these two by drawing the diagrammatically representation and as well as the state representation, and then finally you have to ponder on the questions given. So in the question they are asked to write the code. Code should be in terms of 1011 sequence detector. So as the name indicates, sequence detector, we have to instantiate in our code should be initialized based on the module keyword, instance name, and then the port list. After port list, initialization of the input and as well as the output. So what are the inputs and what are the outputs? So you can write easily inputs and outputs based on the circuit diagram or based on the block diagram that you have mentioned. So from the block diagram, mention the initialize the inputs, outputs, and then what is the case sensitive. Okay, so in what way, in which language or else in which level you are going to write your code. If it is a behavioral modeling, then remember that always at the rate. If it is a data flow or gate level modeling, remember that assign by using the assign keyword. Okay, after writing that, then slowly you have to write your code in terms of the conditional statement by using the conditional statements, if else if, or else by using the case statements. Why? Because we need to achieve 1 0 1 1 in the sequence detector. We need to detect the bits in a sequence manner, right? So first we have to detect the 1, and second we have to detect 1 0, and third we have to detect 1 0 1, and fourth we have to detect 1 0 1 1. So sequence manner you have to detect the bits, okay, based on the conditions. If not, else what? Okay, if not, else what? So finally, after getting all these 4 bits, you need to end the case, then end begin, end, and then finally end up with this end module. Okay, so this is how you have to write the code. I hope you all got this particular problem based on the FSM 1011 mood detector. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.